This is video 2 for the circuits unit. Let's start by talking about current. And let's go back to our reservoir example. So let's say I have a reservoir, or I have some pond, I have some reservoir. I'm pumping water up from the pond into the reservoir and then allowing the water to flow from the reservoir back into the pond. So I've got water coming in and water going out. The water molecules represent electrons. So what current is the uniform flow of electrons. So if I wanted to get the current of the water here, I would simply count how many water molecules pass through the pump per second. That'd give me the flow rate or the current. Same thing with electrons. If I were to count how many electrons flow past a point in the wire per second, that would give me the current. So we measure current in terms of amps. So that's going to be coulombs, the unit of charge, per seconds, the unit of time. So looking at the water tower analogy, the current would be determined by the speed of the water in the pipes. Electrons behave in a similar fashion. Now, what this means then is that we cannot have any breaks in the path. If there's a break, the electrons will stop flowing. So electrons typically flow from the negative terminal of the battery back to the positive, because electrons are negative and they're attracted to something that's positive. Conventional electric current, however, goes from positive back to negative. The reason for this is because we came up with concepts of current before we knew anything about electrons. So the way we define current is the path that a positive charge would take. So we always, when we draw circuits and map out how the current goes, we always draw this from positive to negative, which is the opposite that the electrons would actually go. The next topic is resistance. Now, the circuit that in the previous page would be very, very dangerous to build, and by that I mean the one where we have a battery and then a wire going between the two. The magnitude of the electrical current would be very, very large, and we would actually call this a short circuit. It releases the energy being released is very dramatic, and basically what would happen is that wire would catch on fire. Now we want to regulate the flow of electrons by slowing them down. So to do this, we use something called a resistor to resist the flow of electrons. Light bulbs are a great example because a light bulb is a resistor. So taking a look at this circuit here, we have a battery or power source, and then here we have a resistor. We sometimes call this an electrical load. So as those electrons pass, or once we close this switch, electrons will begin to flow through the circuit, and the light bulb will slow those electrons down because it's converting the electron's kinetic energy into light energy and thermal energy. Now a short circuit would be if you were to take a wire and attach the wire here and here. So that would be a short circuit. or a short wire or short in the wire. And notice that it has no resistance. So if I were to do this, electricity would stop flowing through the light bulb. Electricity follows the path of least resistance. So if I were to put a short in the circuit, electricity would stop flowing through the light bulb and would begin flowing through this short circuit or this wire. And the wire does have a little resistance, so it heats up and that wire can melt. So shorts are very bad. They can cause electrical fires. Going back to resistance, we measure it in ohms. We use the capital omega symbol for resistance. If I wish to calculate resistance of, let's say, a wire, I would take the resistivity, which you'd have to look up, times the length of the wire divided by the cross-sectional area of the wire. So very long wires are resistive, very skinny wires are resistive, short, thick wires are very non-resistive. Now in the circuit, notice that when the switch was open, no electrons can jump across and the current will not flow. That's because air has a very, very, very high resistivity. The term load, so before we called load the external torque placed on a motor. Here, load refers to something that resists electrons, and it's kind of similar. When we draw circuits, we use specific symbols for the diagrams. This is just a quick little list of some of them. For instance, we've got wire, switch, if the switch is open or if it's closed. Resistor, we use a squiggly line for that. A single cell or a battery. Ammeters, voltmeters, fuses. Now, this one for the light bulb, I generally don't use that. The way I like to use a light bulb is I think of a light bulb as a resistor encased in glass. So that's how I like to draw a light bulb. Now we can start talking about some of the math with this. First off is Ohm's Law. So the relationship between voltage, current, resistance, it can be summarized by Ohm's Law. Ohm discovered that the amount of current in a circuit is directly proportional to the voltage established across the circuit and inversely proportional to the resistance of the circuit. So what that means then is that current is voltage over resistance. Or I can say I equals V over R. And that's Ohm's Law. So far, the given circuits have had constant resistance. We call that ohmic resistance. So in other words, we'll get twice the current for twice the voltage. There are non-ohmic resistors, but we won't address those in this course. Electrical power. The moving charges in a circuit or electrical current do work. This work, for example, can heat a circuit or turn a motor. The rate at which work is done, that is the rate at which the electrical energy is converted into another form, maybe mechanical or light or heat, is called electrical power. So the way we can calculate this, now normally power is energy over time. The way we're going to calculate it is to say that power equals current times voltage, or P equals I times V. So an electric oven uses 2,000 watts at 350 degrees Fahrenheit. My lasagna recipe takes about 30 minutes to cook at this temperature. So at 10 cents per kilowatt hour, how much money does it cost for me to cook my tasty Italian dish? Well, first off, I need to convert the 2000 watts into kilowatts. Next, I need to convert my time into hours. Then, since power is energy over time, energy would equal power multiplied by time. So, putting these two together, I would get 1 kilowatt hour. Then I can calculate how much this would cost. So I'd multiply it by 10 cents per kilowatt hour. The kilowatt hours go away, and it would cost me 10 cents. So it cost me 10 cents to bake my lasagna. We could go a little further with this. If we knew the voltage, we could calculate the current, or we could even find the resistance. I'll save that for some worksheets later on. All right, that will conclude video 2.